Okay, I hope this is recording now. We have yeah, okay. Bismillahirrahmanirrahim. So let me begin with this is the SolidWorks interface that you would see once you open it. Or you can go to the help. We have got if in case you have any questions or doubts, you may put in a chat in the chat or come in through audio. We'll stop there and continue from there. It's going to be like going over the tutorial in SolidWorks, which describes how to do the stress analysis, basic stress analysis. This is something like a first pass. If your material passes through the stage, you can do a comprehensive analysis later on. But it needs to pass this, or you need to judge whether your design is okay or needs a lot of improvement after running this particular test. So we simply go to the help menu option here, clicking on tutorials, and then you have got, are you seeing the pop-up windows?
Yes, it's a bit.
Okay, great, thank you. We go to all SolidWorks tutorials. We have got under this SimulationXpress. So when you select on this one, these are three different tutorials that have been mentioned in here. One is the examples where you solve based on the concepts that you learn in the first two. So I'll go more into the first two. The last one, maybe one example or so. And if time permits, we can run through the other examples as well. If not, at least one example to illustrate how this is being applied there. Of course, the first two also involves some examples in there, which gives you details about some functionality and some ways in which you can use such tools in SolidWorks. So if in case you have under tools, you have got add-ins, you have SolidWorks simulation running, you have to uncheck that. We are not using the simulation part, we'll be using SimulationXpress. So we start with the simulation basic functionality. In this one, we will learn how to start the SimulationXpress. We look at the basic steps of design of any design analysis. Okay, so it gives you a predefined procedure how to go over these steps one after another. You don't have to remember, or you don't have to get confused whether you have assigned those loads or fixtures or not. It gives you in a sequential order the design process. So you can just follow the steps given in this particular SimulationXpress. Then we look at the safety of the design. We try to evaluate how accurate those results are, and then finally make a report or document the project. So this is what would be described using a hook. This is made of alloy steel, and it's fixed at the circular hole that you have in here. This is the fixed end, and the load is applied onto the faces, the green faces that you see at the bottom here. 1,500 pound force on the faces that are highlighted there. So in the same direction of the arrows. So this is what is the problem statement. We need to analyze and see whether the material that we are assigning in here is safe enough to take up that load or not. So when you click on next, there's at the bottom right corner, you have got next topic. As you keep clicking on this, it gives you step-by-step procedure, how you have to go over this in solving it. Click on the folder or click the hyperlink that's provided here. This will prompt you to open up the files that are already stored, which came along with the installation of this software. So this file is already made, provided to you by SolidWorks. We are going to use this as it is to do the analysis. Click on next. So it tells you that you need to change the unit system, also try to see what kind of results you're looking at and so on. So I'll just, instead of reading over it, we can change it from here. The unit system will use English system IPS. So I'm going to change it here. This is what it is recommending us to do. We have got, now the next one is to apply the fixtures. So before I go over there, I would have to start the SimulationXpress. So in the previous step, you can see in here the SimulationXpress analysis wizard is shown in here. One way, if you don't find it over here, it would be under evaluate. If you go in here to more options, you have got Simulation Express analysis wizard. In case you don't know where exactly these tools are, which are being indicated here in the SolidWorks tutorial, you just click on the icon and it will take you there. So you have I'm clicking on this. It opens up automatically the evaluate toolbar and lists here the Simulation Express. So this is how you can get to know where exactly those are positioned. These particular icons, whether they lie in evaluate or some other toolbar, can be easily located in this manner. So you have got an additional task pane coming up in here. This is a tool from the task pane. This is Simulation Express. I'll leave this for your reading. You can simply go to the next options. Under options, we can make sure that we save our results. Click on browse, and then maybe I'll put it under folder here. Okay. I've made this folder for this session, so I'm saving it in here. We have English unit system. Okay. Click on next. And now in the task pane manager, you can see in here the steps. These are the 6 steps that we go over design analysis. The first one is to assign fixtures, then loads, assign a material, run the analysis, you get the results. If you want, you can optimize. So these are the 6 steps which are to be followed in a sequential manner to perform this analysis. And this goes with other analysis types as well. If you want to perform any other analysis, this is the order in which we do the simulation. So we have fixtures. So in this case, it was the hole that you have in here, the interface of the hole that needs to be fixed, which means that it acts like a rigid body. It won't have any motion along X, Y, Z, neither it would spin about these 3 axes. So that's the meaning there, that this is completely fixed. And you need to be careful, like what type of fixture you are assigning, like it's a fixed hole. So the regions around it might have some kind of adverse results. There's another one here, fixed versus supported. You can just click on this and look at the animation that is being shown. So this is just a supported one. It is not completely fixed. That the part in the middle there is not completely fixed. It experiences some kind of force as the other part moves. And there's another one which is attached. You have got bolts which are attaching a part onto the base plate. So again, in here, we are using the attached part, so which will allow it to have some kind of deformation along with the main part. So this, you should be clear whether it would be completely fixed or supported or attached parts. So we click on add fixture. So it's all in this pane here that we keep adding those details, going by the steps as being guided by the SolidWorks tutorial. We click on add a fixture. We have got in the property manager over here the face to be selected. I would select the inner face of the hole. It's once it is selected, click. This is the rigid body. Select OK, and under fixtures you would see fixed 1, indicating that one face is fixed external. So we go to the next step now. Click on next, you switch over to load and you can see a check mark coming next to the fixtures, which means that you have completed the first step. You are still remaining with the other steps to complete this analysis. In the next step, it is specifying us to put in a load of 1500. So on the faces as selected here, so I would click on add a force. You can also go in with the pressure, but this example here describes with a force. So I'll select force. We pick up the faces on which the force is to be applied. It is in the selected direction. So I would change from normal and click on the radio button for selected direction. Put in the value here as 1500 pounds force, and in the direction, selected direction, click on the you need to expand this design tree and select plane 2. We have got a top plane, plane 2 parallel to that, and it helps us in deciding the direction. Now they are all pointed upward. We need to reverse this direction. So check the box for reverse direction and put it downward with a force of 1500. Accept this. And you can see in here under external loads, you have got a force 1 giving an item that the load is also applied and a green tick mark next to the load. We move in further and assign the material. So click on next. So the next step is the third step in the sequence here, material, and an alloy steel is to be assigned. That was the given condition or given requirement. So we would assign this from the material library. So click on choose material. So you'll have in the material uh, library, you have got a steel folder. Expand this, go in and select alloy steel. The properties of the alloy steel will be assigned as given in here. You may refer to the yield strength. This is the one that we will be using later on. So this value would also be shown later on, but this is what you can look at for the design for this particular design analysis. Click on apply and close this. So the material line is also checked. This has been assigned. You have got a Young's modulus, a yield strength value coming from alloy steel. So if in case you want to change, you can click on change material and replace this with another one. Click on next. We move to the run. And now it's the time to analyze this model. So you may click on run simulation. This is going to apply the loads. It is going to create a mesh and then run the analysis. Now it is showing you an animation. The analysis is complete. It has applied the loads, and we can see that it is fixed on this end here. It is free to move on the other end. With the load applied, it is deflecting by this amount, and then there are some kind of stresses being developed inside. This is the animation that is being played. If it is behaving the way it has to be or in a predictable manner, you can accept this and click on stop animation. The run is completed. The results are also shown in here. So we go in and check the results now. So we click on yes, continue, because it deforms the way it was expected to deform. And here we have got one Mises stresses. So you have under results, one Mises stress, displacements, deformation, factor of safety. So wherever you would like to see the factor of safety, if it is below 1 or whatever value you would like to keep as a benchmark or a reference, you can put in here. So you have on the right hand side here, say 7.568. So let's see what's the current factor of safety. I would try to go in here in the stress. The results that you have as stress, one Mises stresses. Double click on that. You will be able to see the stress plot. So you have got a scale here with the von Mises maximum stress that you have and the minimum stress. You can play it in animation. So right click on stress, click on animate, and it shows that when the load is applied, the maximum stress, the red color region that you see in here, is appearing somewhere in the middle of the hook at this particular location. So its value is somewhere around 1.189. These numbers are, it need not be the same every time you run, or the ones that are being shown in here on the right hand side in the tutorial. There might be some small deviation, but this is only for illustration purpose. So you have the red region here with the value 1.189 e to the power of 4, whereas you have the yield strength value as 8.998 e to the power of 4. So if you look at these two numbers here, 1.189 is smaller compared to 8.998. One Mises under one Mises failure criteria, if you have a stress value in the material more than the yield strength or equal to the yield strength, the part will start to yield, which will start to deform permanently. So we would try to keep this maximum stress that is induced in the material to be lower than the yield strength value. Then we assume that we are under safe limits, and we calculate the factor of safety by taking a ratio of the maximum stress that you have here over the yield strength that you have. Now, no, it's the other way around. I'm sorry, the yield strength that you have here, 8.9, and if we divide it over 1.189, we are going to get a ratio. That ratio somewhere around 7 here, 7.644. This is what is the factor of safety. If this path is to fail, you have to apply a load which is 7.644 times the 1500 force that you are applying for it to fail from that particular point or permanently deform. So this is how the stress plot is generated. You can just stop this animation, say, okay, go back and check the displacement. You have got just double click, you'll see the displacement here. This is since we are using English system, this will be in inches. Maximum that we can see in here is at the tip here of the hook, which is 1.307 times e to the power of -2. So this is going to be 0.013 inches. Very small displacement that we see over here. So this is in short the results that we see here for stress analysis on a simple hook. So we have gone over these steps as shown in here. We now move to the next step, which is to generate a report. Done viewing the result, click on generate report. If you want to fill in these details, you can add here like description, which is what the study is about and so on, conclusion, and your name as a designer or the organization for which you're doing this, address, and other details. Look at the path where you would like to save this and click on, let me name this as it is trying to create these images from different stages of the analysis and then document in a Word file. So these are all images that are being captured. Once this is done, it will give us a Word file. So I'll leave it for it to complete this. All right, the report has been generated. This is how it looks like. The date on which it was generated, the title that we have given, the table of contents. We have this as a static analysis, so analysis type mentioned in here, and the study name also specified. Then if any assumptions you can fill in here, model information, you can describe about the model. It gives you the 3D image with its volumetric properties and the material properties that were assigned. We took it as alloy steel, so it has pulled in the data from its real database. Fixtures, the same as what we have put in, just one fixture there, and the location has been indicated in the figure. We have the forces, force, the mesh information. This part was the meshing wasn't shown clearly over there, but in the next step you'll understand a little bit more. It was split into small segments. This is how it looks like after it has been meshed and the analysis performed on each of these elements. You have the results here as result with respect to von Mises stress criteria, the minimum value that we have and the maximum value that we have as a stress. So these are the numbers that you have in blue and the red. By the way, there is a sometimes we might get misled by looking at the red color in thinking that it's the point where it's going to fail. That's not the case always. This scale here, blue to red, is only to indicate maximum and minimum. The maximum that you have as red, minimum as blue. You need to compare this value with the yield strength to know whether it will fail or not. This is something you should be clear, should be clearly understood to have a proper interpretation, understanding of the analysis that you perform. So in here, the maximum that we have as red is 1.189. Yield strength is 8.998. This is much higher. The same is the same exponent here, so it's much higher. So it's still in the safe limits. As long as it doesn't hit this red line, that the red color that you see, it doesn't hit the value 8.998 and stays below that, it is considered safe. As and when it hits 8.998 or goes above that, it starts to yield or deform. That should make things clear. You have the result displacement plot here. we have seen the plot in the SolidWorks interface. Then we have deformation plot. Finally, the factor of safety. You can change this factor of safety 1. I've kept it as 1. So all these regions, they are indicated in blue. It means that the whole surface in the of this particular part has a factor of safety more than 1. You can change this value to different number. Let's say 10, for example, and it will show us the surfaces which have that amount, that particular safety factor. You can add more here and keep this as your report for this particular study. So this is the Word file, and all the rest of these are the images that have been included in it. Now, to exit, you simply need to cross the SolidWorks Express simulation out. If you want to save, you can click on yes. But if I want to do that, I would like to rename this. Click on Save As and save it in. I will give it another name because it will override the file that I have from SolidWorks. So I'm giving it another name, and now the study can be saved over there on that new part. Okay. So that completes the first tutorial that we had under this. Now comes the second one. Is there any question before we move on to the second tutorial?
Doctor,
Yes.
the safety factor here, as our instructor said, that the safety factor is defined using the yield strength.
Mhm.
How can we change this criteria to be ultimate strength, for example? In the
But
safety
it's
factor graph.
if you know the from the material properties. From the material properties, you can get to know the value for ultimate tensile strength. Like alloy steel has got yeah, for the elastic modulus. This is the use. If you are having the ultimate tensile strength value, you can then look at the maximum stress that is developed in your part, take a ratio, and then that becomes the the way you're calculating it as factor of safety.
Yeah, but that will be manually. But I mean the graph, the factor safety graph, which you made it less, or it should be more than 1. There is a blue. All of the shape was blue.
Yes.
That's the safety factor heat image, I think, or something.
There was yeah. If you look back, there was let me see if I can open this previous study. The study was already completed, so we can simply jump over to the step where you have this. By the way, it's coming up in the next tutorial as well. But since you have asked, let's go ahead with this. Here you can specify that number. Now, factor of safety, if you're taking it with respect to ultimate tensile strength, as you're saying, then you need to get the difference of the ratio that you will have between yield strength and the ultimate tensile strength. Okay? And accordingly, you have to assign a number here, which would give you the safety factor of safety in terms of ultimate tensile strength. So you can do it that way. This is a quick step, but if you use the simulation toolbar, maybe you have more options there. We can keep that for another day. This that's another complete study. So for now, it is the ratio that you can put in here that would help you. Let's see. Like what would be the, let's take it with an example here. It was 8.9, so that's about 9. What could be the ultimate tensile strength value?
For steel
Yeah,
alloy.
yeah. So I mean to say that if I use 1, it would reflect 8. Let us assume, I'm not saying that this is the number. Just give me a number above this value. Any number.
The
This is 9.
tensile
This is 9. Give me any number above this.
above the 10.
Okay. Then to be a rounded number, let's take it as 16, for example. Then in that case, it is double the yield strength value. Yes. So
Yes.
these are all illustrative numbers. They're not the exact numbers. Making it clear. This is yield strength 8. So if I'm calculating the factor of safety with respect to this, I'm using 1:1. If you're saying it is double, then I should be using 2 here. Okay. Factor of safety as 2, and then say show factor of safety where it is below 2. So this is the entire phase is okay with 2, which means that I know that this is being used with reference to ultimate tensile strength. I can mention that this number here is with respect to ultimate tensile strength, which is actually you are actually using 1:1 factor of safety with respect to ultimate tensile strength. You need to take that ratio between these two and indicate that this map corresponds to the factor of safety related to ultimate tensile strength. Are you getting it?
Yes, yes. Thank you.
Okay. Now we move on to the next part here. This is okay, in this, we try to save material or remove extra material. If we find that there is a part on which we have performed this analysis and we get a safety factor very high, so which means that you're using unnecessarily extra material which could have been saved, and still the part performs the way you would like it to perform. So this analysis would this tutorial will tell us how that would be done. So I'm going to select this particular part. So again, in here we get this part as provided by SolidWorks. Once you have opened this, click on Save As and give it another name. Give it as E3, and I'll also save it in a different location. Now we assign material, and this time we are going to assign a custom material, which is not available in the SolidWorks material library. So for doing that, these are the material properties that we have to assign. We have to change the elastic modulus 0.3 as the Poisson's ratio, yield strength, and mass density. By the way, you can also change it here, and then it would appear there as yield strength, which will be equal to the ultimate tensile strength, and do the analysis. But you need to make sure that in the report that you generate, you change yield strength and replace this with ultimate tensile strength. Wherever you see the word yield, replace it with ultimate tensile strength. Hope you're getting this point. You will understand it as I explain this. If in case you are unable to understand, let me know. I can go over it again at the end of this session. So we are now trying to assign a new material to this, which will have properties as assigned in here. And since most of these units in the library are in MKS system, we'll try to put them as MKS. So I have here custom units, MKS, and we have okay. Click on next. We go to the edit material. So edit material here. In the close collapse this folder here for the steel, which is already open. You can even collapse the category here, which is SolidWorks materials. Right click somewhere there in this pane, click on new library and give in any name. In this case, it says new library, so I would put that as the same new library. You can give a name like my materials or custom materials. Custom material already exists, so given another name which is not available here. New library. Click on save, so it gets listed here. Double click on it or right click on it and say new category and give it another name here. This is it says steel-like materials. You can click pause and then again click on it. It allows you to rename these categories here. Then we have to get the material properties. So we try to, instead of giving it manually, we try to copy the alloy steel properties and then update that. So we go back here to SolidWorks material, open up the folder for steel, select alloy steel, and then simply right click and say copy. Collapse the folder for steel. Same for SolidWorks materials. Go in here, steel-like materials. This is the new category that we just added. Right click and say paste. So you have alloy steel. So let's not have same name in two different libraries. So we'll try to rename this as given here. It says steel-like. Okay, we have already given that. So this is like steel one. It's your choice. You can give any name there. And then in the properties values that you have here, we have to replace it with the numbers given here, 1.2 instead of 2.1. So you can replace this as 1.2. 0.3 as Poisson's ratio. We have mass density to be changed to 7,500. There you go, tensile strength. If you're still there in the meeting, you can change this value here. This value we can get in here for the yield strength. Okay, we have this value. You said about 10 and we took 16 as the example, but the value here is 72 and we were working at 6 or 6.2. So it should be 7.2. So anything else to be changed? Yield, that is 5 e to the power of 8. So we will make this as say apply and then we'll close this. So new material has been assigned. This is steel one. The properties have been assigned to it. We are simply going to go to options. You have got unit system, MKS. Okay. We go to pictures, so we have to turn on the SimulationXpress wizard. Click on next. It's here. the options. You can change the units here. This is the folder where you are going to save your files. Click on next. And for the fixtures, you can see in here material is already assigned. We are assigning the fixtures. We would like to fix this face here inside. So click on add fixture. Select the inner face. That's the rigid body that we have. And then we apply loads. The load we are going to apply here. So click on next. It says that apply it on the upper semicircular half, the force to be as 4,000. So I turn around and then select the upper half here. It's already split the surfaces. We have click on next, add a force. The face was already selected, put in the value 4,000. Selected direction. And then we okay, let me run this and check if we are moving in the right direction. I accept this, move to the next step. Material, we are not going to change, we simply move over to the next step. And then it's the run. So we click on run simulation. Yeah, it's moving in the right direction as expected. So I'll stop this animation, stop animation. And now we can look at various results. So click on yes, continue. We move on to the results page. Now, as you said, we can change this factor of safety 6.49. This is what it's being indicated there. Now it gets updated, factor of safety 6.49. So all of these spaces that we see here are blue, which means that it has this factor of safety 6.49 on all these surfaces. Now let us change this to 8. And now it shows that these are the critical surfaces which will start to deform if a factor of safety is 8. This area is experiencing stresses which will have a value less than a factor of safety 8. So you can go in and check in the stress plot and click on animate. While it deforms or bend displaces, you can see that the red region is forming in this particular segment in here at the bottom, okay, with these stress values, which is 7.699. We put in a factor of safety 8. This has 5 e to the power of 2 as the yield value, and this is 7.66 e to the power of 1. So if you take a factor of safety 8, then this value would be closer to this or slightly above this. That's why it is getting red and is indicated as critical region with that high factor of safety value of 8. Okay. Something around 6.49 or between 6.5 to 8 is good, or we can say 6.5 is safe. Anything close to 8 is going to have some kind of deformations there, which is above the safety limits. Now we know that that's a too high value. We can remove some kind of material here and do some kind of optimization in terms of material. So it says that remove the portion that has already been made in the middle here using cut extrude. Edit that feature and make it through all. So we'll stop this analysis here. We'll go back here into the design tree, feature manager design tree, cut extrude to. Right click and edit this feature, make it through all cut instead of line through all. We need to rerun this part again. We go to run, and now we see the updated model. And now we are going to run the simulation again. Just click on this step here. You'll go back to those steps. So I've clicked on run, so I've been pushed back into run, and the previous results have been removed. All right. Now we see the stresses here. Again, here you can see that it is still within the safe limits. And now is the maximum displacement 0.77 millimeter. So that's the value that we are getting in here as the maximum displacement. Don't go by the image that is shown in here. Look at the magnitude, and if that's within the acceptable limits, you can accept that. Then it's about generating the Word file or the drawing file that you have in here. You can generate by clicking on done with viewing result and generate. Okay. There was a point that I wanted to discuss here, which is and we can cover that in the examples that come up in case we have missed something. All right, so this completes the basic background, what this analysis looks like, what are the steps to be followed, the way you have to do. I hope you are now familiar with the design steps, your design process steps, and how to assign it. Let's look at some of one of these examples here, and I leave the rest for your reading. You have anchor plate, spider, link, and faucet. So these are different parts that have been provided, and we do the analysis on this. So let me close this current study. Anchor plate, for example. Okay, the part has been provided of the clamp that is shown in here. It's made of nylon 6x10 plastic. It's a plastic material, and it says it has 4 holes. The force is transmitted to the anchor plate by the bar component. So there would be a bar component that would apply force on this particular region here. And it says that the maximum force, you have to determine the maximum force the anchor plate can support while maintaining a factor of safety 3. So this material requires you to be having a factor of safety 3. So we need to determine the force that can take maximum force. So let's try with this. The first one, opening up the analysis. We have it gives you the guidelines. Restrain all the 4 holes. Apply force of 350 pounds, and then perform the analysis. Okay. Oh, what's the unit system? Pounds. Saving this as another part here. These are our fixtures. Add a fixture. So it's going to be fixed at all these 4 ends or 4 holes. We have force. So move next, add force on the face here. This is 350. Can even select the direction and say the front plane in this case. It's moving out, so reverse the direction it pushes in. Apply the force. Let's run the analysis. Material nylon. So we click on edit material. Go in SolidWorks materials. Library, you have got plastics as the category, and then select nylon 6 by 10. And that is the material that has been assigned. You have got the yield strength, Young's modulus in here from the database. Click on run simulation. First 3 steps completed. We are going to the 4th one. Yeah, this is how it would try to deform. It's the expected behavior when you're applying force here. It's going to get deformed. The back end getting pulled up from the bottom. It's being held from these 4 points. So this is okay. We can stop this animation and look at the results. This is going to be 1 minus stress here, which is yield strength 2.017 e to the power 4, and this is 8.935. Okay, so it's safe, and if you want to get the calculations, it says that it's clear. It's the same formula that we have been using earlier. So M, let's say factor of safety is M. The anchor plate starts to yield as the magnitude of the force changes from the scale, the factor of safety times that force. Okay. So in our case, it is 3 that is to be the minimum factor of safety that it should have. So maximum force that it can take would be that factor of safety MF over 3. So what do you think is the factor of safety here? This is 8.93 for the figures that we are getting in here, and 2.017 times e to the power of 4. What is M here in this case with these values?
Should be less than 1.
No, like you have the yield strength value 2.017. If you divide it by this number that you have, 8.935. Okay, you're going to get a number. Okay, so you can see if 256. You just take a ratio 2 times e to the power 4 divided by this number. That would give you the M. Okay, so we have taken a force there 350, multiply that and divide it by 3. That will give you the force that at which it is going to have a factor of safety 3 with this material design configuration and the material that we have selected for this particular part. Okay, that's the meaning. So whatever is the maximum force that you can apply would be obtained by that particular calculation. Okay. There was a point that I was just mentioning that I couldn't recall. It is like optimization and making sure that not exactly optimization, but making sure that the results are accurate. So in this case, what we do is we go back to the run here. Or we can say optimize. Let me go to run. Change settings. Change mesh density. Okay, it will delete the previous results. In the mesh density, it's currently in the middle here, coarse and fine. So we saw the mesh density earlier in the report with those elements placed on the surface. We are going to make it very fine. Slide this slider onto the right, making it as a very fine mesh. So we'll have more number of elements coming in there. Now we are going to run it again. Okay, so stress is, let's look at the stress plot. This is 1.076. Earlier it was 8 point something. So there's small variation. Okay, and if there isn't much difference between this number and the previous number, we can look at the ratio. It's like how much 1 and that was 8. It's about 20%. So it should be in an acceptable limit. Okay, not a very high variation. As it gets below 1% or close to between 1 to 2%, the variation on the value that you're getting here, it is said to be accurate. Okay, so it's advisable to go with a finer mesh, but it would take more computing power, and also it would take a longer time to get solved, especially if it's a complex problem. This is a simple part that you have here, but if it's complex, having a larger surface area, joints and so on, it would take longer time. So we prefer try to have a finer mesh until the point where you get a saturation, or until when you don't see any difference in the stress value that is being reported here. Okay. We stop at that point. We don't go further refining it, because there's no point as you're getting accurate values or same or similar values close to that number. That is the meaning there. This is one thing that you have to check when you do the analysis. You try to make it fine and make sure that you're getting accurate results. Yeah, because if there's a big difference and you go with the initial coarse mesh or somewhere in moderate mesh, you may be reporting wrong results. We have this is about the first part. So let's look at the next one. Any questions for this particular tutorial? All right. No questions. We'll start with the next one here. This is about the spider. Okay. It says that you need to have the outer holes of this fixed. Another condition in which we have only 2 holes fixed, and the last condition only 1 hole fixed. Okay. It's made of alloy steel, and the force is being applied in the central hole that you have here. Okay. Okay, let's open this. What's the system? So we change it to IPS. Click on next. And now we apply the fixtures. The 3 outer holes. So we select this inner faces here of the 3 and make it fixed. Click on next. and apply the load. Actual force of 500 pounds. We select this. Apply load. This is the actual direction, and we apply 500. Now the material, alloy steel, already selected there. Okay, it's reforming in the way we expect it to. Stop this animation and continue to the results. Okay, it says that we are getting a factor of safety around 6.1 based on the current parameters that we have specified. We can rerun this with the other options, like it says 2 auto holes fixed, 1 auto hole fixed. We can see that it's yielding 8.998 e to the power 4 is the yield strength, and this is 1.475 e to the power 4. Much lower. So we will try to change this now by going to the fixtures, and I would remove one of the fixtures here. Let's say this one here. Edit this and remove phase 3. Loads are there. We would simply run this. And let's play this animation. It would start experiencing some additional stresses because the other end is not fixed. Yield is 8.9, and then we have earlier this was much lower. Now it has become 5.34. The stresses developed are more because one end is not fixed. Now we go back and change this fixtures again and remove one more phase from the list here. Phase 2, for example. Let's remove this and now see the effect. Now you can see that you have got a value 1.275 e to the power 5, whereas the yield strength value is lower, 8.99 e to the power 4, which means that this part is going to break. If I zoom in further, I can see some red zone coming in this particular part. So it is that at that particular part, you have extremely high stresses beyond the yield strength value. Its factor of safety has also gone down below 1. This is 0.7. So it means that this part is going to fail with the amount of force that we have applied here from this particular point if the other two ends are not fixed. So this is how we have just gone over different scenarios and have looked at the same spider being safe if you have all 3 fixed, 1 or 2 fixed still within the safe limits, but if only 1 is fixed, the other 2 are free. When an applied load is in the center hole, it's going to experience permanent deformation. Now moving to the you have got the next one as ink cartridge assembly. So this is in this you're going to have new material properties that you have in here, and then you apply forces. It's the same procedure for the cartridge ink cartridge. Okay. Okay, is it clear until now? Because we are left with one last uh, tutorial. Just want to make sure that you're able to get the idea how to do the simulation. Or we can pause a little here and then take questions if you have, and then get back to this. Any questions, anyone? No questions. You want me to continue with this, or we stop here?
Victor,
Yeah.
can we perform this analysis on assembly?
Yes, you can do that. Do that as well. And for that, it is like you go into. So I would go to tools, add-ins, and then use SolidWorks simulation. Okay, this is more comprehensive. You have to turn this on. When I check this box, say OK, you would see a new toolbar coming up here that is for simulation. If you want, we can schedule another session for that. This is simulation. This is the toolbar which will allow you to go in to perform new study. Click on new study. It will help you making an analysis for stresses, general simulation for static, or you can choose other type of advanced simulations like thermal, in which you apply some temperatures as loads rather than forces or pressures, and see the effect of that temperature gradient as it moves through the part. That kind of analysis, thermal analysis, is performed. Buckling or fatigue, if you're applying cyclic loads, you're pushing it in, pulling it out, you keep doing it over several cycles. What would be the effect of it on the material? That is fatigue analysis, and so on. So there are many test or simulation analysis that you can do in here using the simulation toolbar, in which you can also do the assembly analysis on an assembly. So you have a part, or you don't have a part here, you will have an assembly opened up, and then you would go into simulation toolbar and select the type of simulation or study that you would like to do, and then perform on it. The procedure remains same. Like you'll have to, let's say if I select this one and say, okay, I'll have to again specify details like what is the fixed elements of connections, the say fixtures. Then you have external loads, meshing, and then the result options. So order is same. If you understand this, you can easily get the other one and start doing it on your own. But if you want, we can take up that as another session. That would make it too long for this particular session. Any other question that you have? For these two examples, I would leave that as a reading assignment. If in case you have any questions related to it, we can take it up in the another session. If interested, you can pass on your feedback or comments to the club, ME club, and they can organize another session for this particular toolbar, which is simulation, a comprehensive study, okay, on assemblies.
Okay, thank you.
Okay. Anyone else here who has any question? All right, so shall I go over this? Let's see what it has to say. I would turn off this simulation here because I cannot perform two together. So it's SolidWorks simulation. Earlier it was like you can use one of these two. Now we have evaluate SimulationXpress. Click on next. The good thing about SimulationXpress is if you're new to this, it gives you a step-by-step guide or procedure that you have to follow. Like when you click on this, you have got in the task pane here the fixtures. You need to assign that, and it then prompts you to assign loads. So it takes you through the process through this procedure. So we add a fixture here. Currently, it says that. Okay, this is the ink cartridge assembly. It's a part in that assembly, and you need to push the arms of the link apart to assemble the component. So these two are to be pulled apart for the part or the cartridge to get inside and get fixed or assembled in there. To simulate this process, you apply forces normal to the faces of the arm, and you need to determine the effect of removing the rib on the maximum force that you can apply on each arm. So there is a rib here inside, which we can remove and see what is the force that would be acting on these if that's removed. Okay, let's try to do that now with these material properties. So I've opened this file and okay, let me first assign this material. Edit material. This is new material. Let me see if I have that from the previous one. I don't have it. So I'll use this copy and paste it over here. It's better if we take the other properties of the material, but what's given in here. Okay, let's go with the number 8.8. Point 3. That same masks density is different. Okay. Now we assign the fixtures. It says restrain the cylindrical face shown in the figure. It's inside hole that you have here, which will pass through one of the bars. Go back, and now we apply outward forces. So this is going to get pushed up when we have a cartridge getting pushed inside, in cartridge pushed inside. And the force to be taken as okay, you're taking you have to divide that load. That's what it says. So let's put a number here. So you have to add force on this face and the face on the other side. I don't see any number mentioned here. Okay, let's go in with some number here first. This is 100 that I have just used and say OK. And now we run the study. Material is already assigned. Run simulation. Okay, it's behaving in the way we expect it to. Say OK. Yes. And the value that we have given is too high. So well, it is 1.19 to the power of -5. This is very high force that we have applied. So you can change the force value here. And now we rerun this. Okay, now you can see in here, this is the yield strength that you have 3.62. We are getting a stress that is coming in these arms, maximum value of 6 times e to the power of 3. So what could be the force that it can withstand? How do I calculate? Any idea? The current force that I have used in here is 2-pound force. So when that is being used, we have a stress of 6 times e to the power of 3. Yield strength is 3.62. So the factor of safety would be 3.62 divided by 6.05. Okay, that factor of safety, which is m here, we multiply with the force. Let's say this force we would like to calculate. In this case, it was 2. So now you know that 2 is too high a force for this particular material that we are using in here. We just need to make sure that it gets down to a value of 3.62. So the ratio here, if you want to whatever value that you get here, divide that the force that you are applying here, divide that particular by that particular number, you'll be able to the ratio that you get here if divided or the 2 divided by that number would give you the force that it can withstand with the factor of safety 1:1. Okay, if you want it to be twice, then divide it further by 2 to get it as the value which of force with the factor of safety that would come on this particular part. Okay. This is how you can do the analysis or get down to a number how much force that particular part that you have made can withstand without yielding or failing. this is one kind of looking at it in a reverse direction. Rather than assigning some loads and doing a stress analysis, you look at the analysis and then determine how much it can withstand. Now, we can even check this by removing this particular rib that you have in here. You can just suppress that particular part and see the effect of it. You have this part here, we suppress it. Let me stop, move on to of this. And now go to run. Now you can see that it has yielded more than the previous one. So the rib was kind of support to the forks that you had here, but now without it, you are getting a higher stress in this particular part with the same set of force values that we have used earlier. This is another example about the link. We have one last example here is of a faucet in which you have some internal pressure being applied, and then that is you select the inside faces, apply the loads, and then see the effect of it on this faucet. So I would leave that as a reading exercise for you. I've gone over 3 of these examples, another 2 explaining the concepts. Anything that's not clear or you would like me to repeat, or any other question apart from this, what has been discussed? Okay, no questions, then we can end this session, and maybe next time we can come up with another topic of your interest through any club or any other club. All right, thank you for attending. See you all next time.